Hello students, today we're going to be working on definite integrals. So let's get started. So in here we're going to talk a little bit about some of the notation and some of the terminology you're going to need to know. So we have the Greek capital sigma, which looks like that weird E. It stands for the sum or the sum of. The index K tells us where to start, and that's located below the sigma, and where to end, above the sigma. Now, you usually see this denoted like you see down below. We see the first example here. It says sigma, when k equals 1 to n, for a of k equal to, and you notice here it's saying basically add up all of those a's. A of 1, a of 2, a of 3, a of ... until you get to a of n. If you look at the one below, this time we gave you k squared. Notice on the bottom of sigma it says 1. That's why we start at 1, so 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. Notice we're adding because it says the sum of. And so this is one thing you're going to be working on, fortunately not for too long because we have calculators. So now we're going to talk a little bit about Riemann sums. So Riemann sums is based off of what we did on that last section. We had RAM, MRAM, and LRAM. All of these are examples of Riemann sums. Now we can use this on any function on an interval, on a closed interval a to b. Now we're basically partitioning the interval into n, or subintervals, and these become the bases of our rectangles. Now we're gonna let's name the x-coordinates of the corners of our rectangles. And so here's how we're gonna use it a little bit more. So we're gonna denote a by x naught and b by x sub n. The corners of our rectangles make the set p equals x sub 0, x sub 1, etc. Now the p is called the partition of AB. So our subintervals are the closed intervals, so we can choose specific portions or subintervals in this partition. And the width of the kth subinterval has width delta x sub k. Remember, delta means change or change in. So when we see delta x sub k, that's saying, look, the difference between x sub k and the k, the one before k minus 1. So we choose some x value inside each subinterval to find the height of the rectangle, which you know. That's how we found the RAM, MRAM, and LRAM. And you could use any other point, but those are the three we focused on. Now, in Riemann sums, the area of each rectangle is the product of its height and its width. The sum of these areas is S sub n equal to sigma k equals 1 to n for f of c sub k times delta x sub k. This is the Riemann sum for f on the interval AB. So all of that work we did on the last section, this is how it's mathematically denoted. Here's the function, here's the change. So every time we found that height, this is how we found it. We substituted into the function, and this was our width for our rectangle. So the definite integral, this is the first time we're going to really look at this, is denoted as I equals the limit for the partition P as it approaches 0 for sigma as k equals 0 to n of f of c sub k times delta x sub k. So I is the definite integral of f over the closed interval AB, and this p is the longest subinterval length called the norm of the partition. So definite integrals of continuous functions. All continuous functions are integrable. Let f be the function on the closed interval AB, and let the closed interval AB be partitioned into n subintervals of equal length. That's the important part. They need to be an equal length. So integration notation. I know I gave you a lot of jargon and a lot of things to consider. This is the part where you really need to wake up and write this stuff down. I is equal to the limit as n approaches infinity for sigma from k equals 0 to n for the function times the change in x. This is what we're going to be using the bulk of the time. We read this from the integral from a to b of f of x dx. So here's a little breakdown. We have the integral sign, which is the integral sign. This is the upper limit of integration here, b. This is the lower limit. This is the function that we're finding the integrand of. And this is the variable of integration. This is what we're finding the integral of, its respect to x. And this is the integral of f from a to b. So let's look at how this actually applies a little bit more. Now, by now, we've taught you how to use the Riemann Sum program, or the RAM program. So I want you to use that program on this function here. What I'm going to do is, because I don't have that calculator that I installed it on with me, I'm going to use a calculator that I found online. It's x minus sine of x from 2 to 6. I'm going to go ahead and do 4 rectangles. And I'm going to do the middle sum. And my answer is 17.435. So that's my answer. Yours should be fairly similar. So what I want you to do now, because we took this really ugly formula, I want you to write it as an indefinite integral. And so the way that would look is we always start off with the integral sign. And we know we have this is equivalent to our dx. So we're going to write that as dx. We know that the integral goes from -1 to 3 because it says the partition here. The function's the weird part. So here's how easily this works. It's going to be 3 divided by 2 minus that c sub k. That's our x value. So now you have your function. That's how we write an integral in the way that we're going to be using it for the majority, actually for the rest of the year. So let's try another one. Hopefully you can try this one without me. The answer should be the integral from negative pi to pi for cosine of 2x dx. Keep in mind, if you don't have the dx, it's going to be counted as wrong. So notice we're just replacing the c sub k with the x. Next problem, or next thing. So every time we've been finding the integral, we've been finding the area of the curve. And keep in mind, when we integrate, we're taking a derivative and we're going backwards. So when we found if we had the velocity formula like we had in the last video, and we take the integral of the velocity, that actually brings us back to the displacement function. And that's why when we are looking for the speed at 55 miles per hour for 3 hours, we could just find the area of the curve, or the area under that line, or area under the curve. So if y equals f of x is non-negative and integrable on the closed interval a and b, then the area is denoted by this here. If y equals f of x is non-positive, as in it's negative, and integrable on AB, then the area is equal to the negative integral from a to b for f of x dx. So let's look at an example. So if I give you a graph like so, and I draw a sine graph here, notice that from 0 to almost 3, the area under the curve is above the x-axis. That means it's integrable and it is non-negative. That means it applies to this one here. If you do the same thing for the bottom equation, or if we look at the second half of this, notice it's under the y-axis. That means if you did this on your calculator, it's going to give you a negative number. So the reason why we use this one is because if you had a negative area and you throw this negative sign in front, it takes that negative area, makes it a positive, because we can't possibly have a negative area. It's just not mathematically correct. So just something to keep in mind. If you get a negative answer, that's why. And you want to throw a negative in there. So for any integrable function, we have the integral from a to b, f of x dx. That's equal to the area above the x-axis minus the area below the x-axis. And that's why we have our upper limit b and our lower limit a. Now, to evaluate integrals, we can use geometric areas to evaluate certain integrals, including constant functions with rectangles, linear functions with trapezoids, and semicircles. So let's look at an example. Here we have the integral from 0 to 5 for the square root of 25 minus x squared dx. Now, I haven't shown you how to find the integral for this yet. So what we're going to do is we're going to go on Desmos really quick. And we're going to graph that. That's pretty much y equals the square root of 25 minus x squared. So if you take a look at this, we wanted the integral from 0 to 5. So what we're really looking for is this area here. Now if you think about this area here, isn't that really just the area of a quarter circle? So if the area of this is just a quarter circle, well then, to find that integral, it's just pi times r squared. So r is 5. Times pi. So our area here is 25 pi. And just for the record, if you didn't know where I got that 5 from, the radius from here to where it hits is 5. Again, I haven't shown you how to find the integral just yet, and that's on purpose, because I want you to see that there are alternative ways of finding this for some cases. So if f of x equals c, so basically if the function is a constant, then the integral from a to b is equal to c times the difference in b and a. So let's do a real example here. So basically, to find the integral of 3 from 1 to 5, we're going to do 3 times 5 minus 1. That's equal to 3 times 4. That's equal to 12. And that's our integral. So let's look at another problem. So the cool thing is that there are alternative ways of finding this. I am going to show you right now how to do this on the TI-83. So if you don't have your TI-83 in front of you, this is a good time for you to take it out and follow the steps. I'm going to do it on my calculator at home. I'm going to expect that you're doing it there. So we're going to approximate the following to 3 decimal places. So on your calculator, I'm going to have you turn the calculator on, and then on the left-hand side, just under the alpha button, I want you to press Math, and then I want you to go to option 9, FNINT, and then it's going to give you the integral sign with some extra blocks. So on the bottom left integrand, the lower limit, we're going to put in -3. On the upper limit, we're going to put 5. Under the function, the part in parentheses, we're going to type in cosine e to the x. And then right next to the d, we're going to put x. After that, we're going to push enter, and it's going to do all of the work for us. When it's done, sorry, mine's still working on it. You're going to get 2.419. So hopefully you got the same thing. We're going to try it again for the bottom one, part B. So here's a little trick. Instead of going through that math button again, you're going to press second enter, and that pulls up the previous equation. And we could just change the limit there. So we're going from 0 to 1 for the function 2x tan x. And then we're going to push enter. And the answer here is going to be 0.856. So now you found the integrals on the calculator. So that's all for now. We'll work on a second way to find this integral on your calculator in class. But that's all for now. I'll see you.